The ideas expressed in the following presentations are those of the speakers and do not necessarily reflect the views of ACI or its committees. ACI web sessions are recorded at ACI conventions or other concrete industry events and will be made available for viewing free of charge for 1 week. Thereafter, they will be archived on the ACI website or added to ACI's online CEU program, depending on their content. You can earn continuing education credits through ACI's online CEU program. Visit www.concrete.org to register. ACI conventions provide an opportunity for networking and for keeping up to date with the latest in concrete technology and practices.
Our second presenter today is Dr. Hassan Saffarini. He's the manager of the Structural Engineering Department of NORR Limited Architects and Engineers in Oakville, Ontario. He's also an adjunct professor in the Faculty of Engineering at Ryerson University and was previously for over 20 years a professor of structural engineering at the University of Jordan. He's been involved in the design of a range of complex concrete projects in Canada and throughout the world. And today he's going to be discussing the unique structural challenges associated with constructing a retail mall underneath the historic Union Station in Toronto. Dr. Saffarini.
Good afternoon, everyone. My presentation today is really going to be about an engineering project. It's more engineering and less research. I hope this would give you a little bit of a break. It is about a project that has been 5 years in the making, and I have been involved in this project ever since it was conceptualized. It is formally named as the Union Station Revitalization Project, and also dubbed as the Dig Down Project, as you will see from the obvious subject of the project and what we are doing. Some of you may have experienced some inconvenience as they travel down Front Street, so I'm just giving a disclaimer. This is not our project. This is an adjacent project for TTC. Our project is totally hidden under the ground, so we are not to blame for any of your inconvenience for now. I will be talking a little bit about the history of Union Station, and I will be talking about the project and what we are doing, and I will focus a little bit about the concrete material technologies that are involved. What you are seeing is the head house of the Union Station. It was completed in 1919 as a fine example of the Beaux-Arts of the period. It is a hybrid steel frame and masonry that had concrete slabs on steel framing only in the ground floor and the basement. Above that, everything is composed of steel framing with flat terracotta arches. Adjacent to this and just to the south of the building, which is the head house building, is a viaduct structure, which is primarily really a bridge that elevates the trains to the level of the concourse. And this was built of a purely reinforced concrete structure. In fact, it was built almost 10 years after the completion of the head house, and that had to do with the issues in terms of decision making in the city of Toronto. Nothing that we have now, so this was only in the past, I guess. All right, so the structure is a Turner flat slab, which has a four-way reinforcement system with bent bars, which are common of the period. It had mushroom columns and drop panels. from this you get some orientation in terms of where we are. What you see is the slice of the head house that is over here. To the south of it is the viaduct structure, and to the north is the TTC station, which is also subject to an upgrade and an expansion by adding one platform. So the site is a heritage protected site and is one of the most significant buildings in Canada, in fact, in terms of its heritage values. We are doing a lot of work on the restoration of the building, but that's not the subject of today, so I will not be discussing that aspect of the project. What I'll be talking about is really the dig down, which you can see, which basically is the entire footprint of the viaduct structure, which is almost 240 meters long, as well as part of the head house that we are digging under, and the moat that surrounds the head house, and we will be at the same level, which is the reduced level of the entrance of the TTC station. So all in all, we'll be digging an area of approximately 25,000 square meters. Well, I'm talking in the past tense. In fact, the project is in earnest for a while, and as you will be seeing. So this just gives you an idea of a perspective in terms of a cross-section. The head house is to your left, the train shed is to your right, and underneath that is the viaduct structure. As we complete our project, we would have created a new retail mall below this structure, and we would have created a new concourse, really, which is a new slab that would be sitting a little bit higher than where the current slab on grade is now. So the concept is explained in this slide. The situation before the intervention is that we have just this one concourse. We are going to be excavating. We're going to be shoring the track slab, and then we're going to break the column, remove the foundation, and then cast a new column with its new foundation, and then cast a new concourse slab. The original viaduct structure was highly underutilized. There was some usage for it in terms of some car rentals and some maintenance, and a little bit of it was used for the by GO as part of the GO concourse, but that was even a very small part of the viaduct structure, so it was highly underutilized. This is again the same diagram, except it shows the sequence of what we are doing and how we are achieving it. So I'll be going over this in a minute, so we'll see it as it's happening now, in fact. So this is an artist image of what we are going to be expecting to see in a few years. We're in fact going to be seeing this as planned in 2015. But you will see more of it as before that, because it will open in stages. This shows the dig down, which basically is the excavation, and you see these pedestal foundations that were supporting the track slab. To support the track slab, we had to support this on firm grounds, and we supported the majority of those on micropious columns that were socketed in rock. And then as we mount these shoring posts, we introduce jacks, 4 jacks at the 4 corners of the column, and use a manifold system to make sure that the loading of the 4 corners of the column is uniform. there was a telescopic kind of post that we used, which had two shafts that once the jacking is completed, welding would be performed so that the load is no longer on the hydraulic jacks, but rather on steel, and then the jacks can be removed temporarily until they are reinstated when we want to transfer the load back to the completed column. This shows a snapshot of one column that has been cut, and where the original rebars are exposed by chipping the concrete around. Couplers are introduced to connect the old round bars to the new deformed bars. We tested this, in fact, and we made sure, since these couplers are certainly not designed for the original round bars, so this was a different application that we had to make sure that it works, and indeed the failure happened in the steel round bars, not of course in the new steel bars, nor in the coupler itself. This is a showing of the formwork that's been done, and we would be pumping the concrete from below, and it's done in two stages. The first stage is the majority of the column, and we just leave a 50 millimeter distance so that we can grout this to make sure that we have the majority or a good part of the shrinkage that takes place in the length of the column before we grout with the shrinkage compensating grout. So this is an image of part of the completed columns, and as we then place the Concourse slab formwork, and we then you can see the dowels that are introduced in the columns with couplers that connect to the Concourse slab reinforcement. This is the Concourse slab as cast from below. We used the same system more or less that was used, except we did not use the column capitals, but we had a flat slab with drop panels, and of course the slab on grade is still on top of the level of the foundations which you see. This is the Concourse slab as seen from above, and it shows the original track slab with its mushroom capital and the drop panels. We were asked that the train station had to be fully operational. There was no stoppage whatsoever, not for even the trial columns that we did at the beginning. And part of running the train station is all of the equipment, and we were asked to produce a room that would house the equipment and not be removed at all at any time, or for the equipment to be moved from that. So what we did is that we cast a slab on micropiles, then dug down below that slab, braced those micropiles. Then we had like a platform that is just waiting with all of the coupling, the couplers on those dowels to receive the rebars for the Concourse that is at that level. Okay, we monitored the movement throughout, and we required an accuracy of 0.3 millimeters and the tolerance of 6 millimeters. This is an example of the monitoring done by a robotic total station, where the movement roughly stayed within the 3 millimeters, not really the 6 millimeters, which was the higher limit that we had set. As I said, there were two pours, and I'll talk a little bit about the concrete mixes. that were used. There were other applications such as column jacketing and repair of spalled and delaminated concrete and carbonated concrete. Again, this is not the subject of this presentation, so I will only touch upon the main subject, which is the column replacement. Part of the evaluation is that we tested the concrete before we started, and then we tested some of the concrete that we retrieved from site as we proceeded. It is interesting to note that the concrete was on the whole significantly higher than whatever was specified originally, and one of the explanations was that perhaps the granular size of the cement of the time allowed a progressive curing for a longer period of time, so that we had this growth of concrete. Now, basically, we had specified sorry, this is just to talk about the same point that I made, that the concrete strength was significantly higher. We did have to change course on some of the reinforcing of some of the pedestals where we had specified carbon fibers. The concrete in those pedestals turned out to be less than what we had tested originally, so we reverted to reinforced jacketing. So basically, the mix design was dictated by the fact that we had congestion in the reinforcement, particularly at the splice. We needed to pump the concrete. We did not have the luxury of doing vibration, so we wanted self-consolidating concrete, which was the answer to all of this. And we wanted early strength because we were doing the columns sequentially, and we did not want to do this for the next 10 years, so we obviously wanted to expedite the process, so there was a limit of how long we can keep the columns jacked before we move on to the next column. We wanted to limit the shrinkage so that we limit the amount of movement as well in the slab, and that was a critical issue. So we used flowable self-consolidating concrete. We used shrink guard to reduce shrinkage, and we specified a 7-day strength of 35 and a 10 millimeter maximum aggregate size, and we used high range water reducing and mixtures. Basically, this is in terms of the self-consolidating concrete, which used a product by Euclid, basically for as a super plasticizer. Then there was the shrinkage aspect, and there was a product primarily by Grace, which claimed reduction of shrinkage by up to 50%. We consistently got the required 35 MPa. However, we improved on the 7 to 28 day ratio, statistically at least. So this is the results of the 7-day strength, where we are almost always exceeding the 35 MPa. The top part, which is the top wall, which is the 50 millimeters, was a Sika grout, and we used in that for the it had a 2-stage shrinkage compensating mechanism. The original had a different kind of mechanism for reduction of shrinkage by limiting the surface tension in the pores of the concrete. That was what was used for the column as a whole. This was what was used for the last 50 millimeters. This is the jacketing that we had used. and we used the carbon fiber for the columns at the top where we had predictable concrete strength. We had other applications such as widening of the mold by complete removal of columns and replacement of those by steel framing. And then we had one case where we removed the columns entirely to create a larger loading dock and replaced that by a story-high steel truss. This is the steel truss in position, and you can see two trusses surrounding any one column. Then we would jack the load onto the truss, break the column by wire cutting it at the capital, and as you can see here, this is the column that has been removed segmentally after that, and they created space below, which is column free. And these trusses were then embedded in the partitions and the concourse above. And that's my presentation. If there are any questions.